I'll quickly do the introductions. So, could Isaac help me to transfer to the next slide? So, welcome everyone. This is a webinar that we are gonna present the result of measurement of cosmic expansion rate using the latest LVK gravitational wave advanced catalog GWTC 5. You can see the archive number linked to our paper, and also there are public links to the DCC page. If you're interested in the data behind the result, you can also go to the data distribution link. All right, let's move to the next slide. Yeah, I forgot to introduce myself. So I'm Xinyu Chen. I'm an assistant professor at UT Austin. I'm a paper manager. Today we are gonna have Isaac McMahon from University of Zurich and Alexander Papadopoulos from University of Glasgow to present the result. And then during the Q&A sessions, we'll also have, could you help me to go to the next slide? Yeah, we'll also have Gregor Piera from University of Rome at Sapienza and Konstantin Lade from Flatiron Institute as a panelist for the Q&A session. So without further delay, let's start.
Okay, great. Hello, everyone. Thank you for your attention. As Shinu said, I'm Isaac from the University of Zurich. Let's start from the very beginning. All right, so what are we trying to measure? We know that the universe is expanding, and it has been for a long time. And we want to know what is the expansion rate of the universe as it is today. And this is quantified through the Hubble constant, which is denoted as h naught. And there are many ways to measure the Hubble constant. And in fact, there is something called the Hubble tension between different experiments that try to measure the Hubble constant. Over the last few decades, we've gotten more and more precise with our measurement of the Hubble constant. And now we have come to the situation where different methods for measuring the Hubble constant give us different results at a 5 or 7 sigma level, which means that this is something significant. And so there's a lot of discussion about what could be causing this Hubble tension, whether it's new physics or whether it's some systematic effect in some of the measurements. But what we are concerned with is that gravitational waves, or GWs, can offer an independent way to measure late-time cosmological parameters like the Hubble constant. So with gravitational waves, we can provide a new independent way to measure these parameters to hopefully provide a new voice into this conversation of the Hubble tension. We can also use gravitational waves to help test general relativity or alternatives to general relativity at cosmological scales at the largest level. So how do we actually do this? We use something called standard sirens. So merging compact binaries like black holes or neutron stars, when they combine together, they emit gravitational waves, and these are known as standard sirens. This is an allusion to standard candles, which are very common in astronomy. What they are is an object that has a known intrinsic brightness, and they emit some sort of signal like light. And the relation between the light you observe and the light at the source and the brightness, this is related to the distance between the source and the observation, right? So a wave, as it propagates through space, loses amplitude according to the inverse of the square root, or the inverse of the square of the distance. And this is known as the luminosity distance. And so gravitational waves work the same way, right? The gravitational wave has an amplitude, and it also follows this inverse square law. So analyzing the gravitational wave signal, which is called the strain, and performing parameter estimation, we can measure properties about the source system of the gravitational wave, including the luminosity distance to that system. And then we can take advantage of something called the luminosity distance redshift relation. So luminosity distance and redshift are two ways that we can measure distance in space, which are slightly different to each other. And they're actually related by the Hubble constant and some other cosmological parameters that are related to the component makeup of the universe, like dark matter, dark energy, and so on. But the one that we're really interested in today is the Hubble constant. And so if you have a measure of the luminosity distance and you have a measure of the redshift for one particular object, you can then get a measurement of the Hubble constant, which is supposed to be global for all of space at the same time. Now, the luminosity distance is easily measured from the gravitational wave data. The problem is the source redshift, which we call Z. The source redshift is, in general, not easily obtainable or as easy to obtain as the luminosity distance from the gravitational wave signals, but there are ways to do it. And so in this study, we employ 3 different methods to measure cosmological parameters using gravitational waves. And these 3 methods are called the bright siren method, the spectral siren method, and the dark siren method. The first one that I want to go through is called the bright siren method. So this one is actually the easiest and simplest case. If you have a gravitational wave that gives you a luminosity distance, and then you see an electromagnetic counterpart, which is associated with that event, meaning that you see an explosion or some sort of object that is one-to-one exactly the same system as the gravitational wave system, then you can also point a spectrograph or a normal telescope at that object or its host galaxy and measure a redshift directly from spectroscopy. And so then you have a luminosity distance from your gravitational wave, and then you have a redshift from the host galaxy in spectroscopy. And then you can directly, with these 2 numbers, calculate the Hubble constant. So this is the simplest way to do this. It's very easy. Unfortunately, we have only done this once, or we've only been able to do this once. There was an event that was a collision of 2 neutron stars called GW170817, and an electromagnetic counterpart was discovered for this event. And so we were able to directly associate a galaxy with a known redshift with the gravitational wave and arrive at a measurement of the Hubble constant. Unfortunately, we have not been able to discover another such event in the years since. And so we have to rely on other ways to actually measure the Hubble constant. The second method that we use is called spectral sirens. This relies on the mass distribution of gravitational wave sources. So there are features in the mass distribution of gravitational wave component masses, and there's actually a relation between what you see in the detector frame on Earth, what you actually observe, and what the masses really are in the source frame, where they come from. And these 2 masses are related by the distance in between the detector and the source, which is the redshift. And so if you have a measurement in the detector frame, you have a measurement in the source frame, these 2 masses are related according to the redshift and other cosmological parameters. So we can take advantage of this. If we look at the population studies that happen alongside our cosmological studies, we can actually fix the cosmology and find out what the general shape of the mass distribution is, right? So through other studies, we know that the mass distribution of gravitational wave sources has a certain shape. There are these peaks that happen, in this plot around 10 solar masses and then around 30 solar masses or so. And if you fix the cosmology, you can plot this very well. Now, this is dependent on the cosmology, which is, a certain value of H naught, a certain value of dark matter density, and so on. But if you change the cosmology, this shape actually changes, even if all of the GW data is the same. So for example, if you increase the value of the Hubble constant that you fix, all of these peaks move to the left. If you decrease the value of H naught that you fix, then all of these peaks move to the right. Now, using this insight, we can actually flip it. If you unfix the cosmology now and you let h naught be a free parameter, you can then actually get a measurement for the Hubble constant that is jointly inferred with all of the population parameters. So not only are you trying to measure what the shape of the population is, but you're also measuring the correlation between the shape of the distribution and the cosmological parameters at the same time. And so this is what we do. We can extract cosmological information from the population of the masses by jointly inferring them with cosmological parameters. And this does allow us to get actually a reasonable measurement for the Hubble constant. Now, the third method for measuring cosmology with gravitational waves is called the dark siren method. In the dark siren method, we're using the same idea as the bright sirens, but in this case, we don't have optical counterparts for our gravitational wave events. But what we do have are galaxy catalogs. These are a list of galaxies that they include like the positions of the galaxies and the redshifts, redshift measurements. And so using a galaxy catalog, we can't do an exact one-to-one association with the gravitational wave event, but we can do a statistical measurement with all of the galaxies that are in the volume of our gravitational wave event, or where we expect it to be. So for example, this is an example event, GW 190814, which is one of the best events that we have so far in terms of volume. It has the lowest volume of all of our events. And on the left-hand plot, you can see the area, the localization area. This is from the gravitational wave data alone. We can tell which direction it came from and how far away it is, but this is still kind of a blob in space. And on the right side plot, you can see all of the galaxies in our galaxy catalogs that lie within this volume. And so what you can end up doing is that you take all of these galaxies, you weight them according to some weighting scheme, and then you make a statistical measurement of the Hubble constant as a weighted average of the Hubble constant from all of these different galaxies. And then you arrive at a broader measurement of the Hubble constant. And so even though this is broader, we have many, many more events that are actually dark sirens and don't have an electromagnetic counterpart. And it happens in this study that the one bright siren event that we have gives us about the same sort of constraining power as the rest of the several hundred dark siren events that all contribute together. And so in the end, we combine all three of these methods, the bright, the spectral, and the dark sirens, to arrive at our final measurement of the Hubble constant. And so we are jointly constraining the population parameters and the cosmological parameters at the same time to arrive at a Hubble constant measurement. Now, let me talk a bit about the data that we use that is input into our analysis. We're using the GWTC 5 catalog. This combines about 4 years of data taking with 390 gravitational wave candidates, which is 161 more than the previous data release, GWTC 4.0. Here in this plot, you can see a cumulative distribution of all of the events that we have discovered so far, according to observing time. This actually includes a bit of a sneak peek into the next data release for O4C, which is the third part of the fourth observing run. But what we are considering in this study is only up to O4B. So this is 390 GW candidates. There are a couple interesting candidates in this data set in GWTC 5, and I've included some of the links to the papers for these special events here. Some highlights include this pair of events, which have unequal masses in spin-orbit misalignment. So these events point towards hierarchical formation channels, which means that we might get some information about how intermediate mass black holes form. Another event, which was GW 250114, was the loudest detection to date. So this event had an SNR of 76.9, which is the best signal to noise that we have had in all of our observing runs. Additionally, the event GW240615 had the most precise localization area to date. And so this had a 90% credible area of 6 square degrees. Now, this is important because for cosmology, we like our events to have better localization from the gravitational wave signal, because then we can constrain the event to a smaller volume and therefore a smaller number of galaxies in our galaxy catalog to get a more precise measurement. If you look at these events on a mass scale, so on this plot, you see the vertical axis here is solar masses, so the mass of the black holes that are involved. The down is lower mass, up is higher mass. And on this plot, each gravitational wave event has 3 dots. There are 2 component mass dots, which are lower, and then they combine with an arrow into a higher mass final mass, right? So 2 combine into 1 that's heavier than the original 2 components. So this plot right now is showing every mass that we've detected up to O4A. And here is O4B. It generally follows a similar distribution, but I do want to say that this is not the full picture. This is not every black hole binary or neutron star binary that exists in the universe, because there's some selection bias that is related to what our detectors can actually see. However, this selection bias is corrected for in our analysis, and this is just one of the systematics that we have to consider. So previously, I talked about jointly inferring the cosmology parameters with population parameters. And now I want to talk about the models that we use to actually say what the shape of our mass distribution is. We explore 3 different source frame mass models. They are called the multi-peak on the left here, the full pop 4.0 on the middle, and the full pop 3 peaks on the right. The multi-peak distribution is a black hole only distribution, so this one excludes neutron stars, and the other 2 do include the neutron star distribution in their model. So these are all parametric models, meaning that they have some parameters that change the locations of the features, for example, the peaks or the shape of the power law. And so these are all parameters that go into our inference in our pipeline, and they're jointly measured alongside our cosmological parameters. One important thing to note is that we assume no evolution in redshift for these mass models, which means that the shape of the mass distribution, the distribution does not change as you go away in distance. This is because there were some studies previously done that suggested that there is no evolution in the mass distribution. So we make this assumption just to make things easier, but we also expect that it's not a significant effect if it does exist at all. So one important thing to note also is that we have 2 multi-population mass models, which include both neutron stars and black holes. So we're combining the entire distribution of masses that we measure with our detectors. Like I was saying, these are parametric models, so they have a lot of parameters. There are some that are more interesting for us because they couple with the cosmology more. And for example, the positions of the peaks, which is the red labeled ones here, like the mu low and mu high. These positions strongly couple with cosmological parameters like the Hubble constant. And so if the peaks are shifted to the left or to the right, this affects and is strongly correlated with the value of H naught. The same thing happens with the maximum mass, which is the upper limit of the masses that can be detected, and the power law index, which is the slope of the mass distribution. So these are the parameters that couple the most with our cosmological parameters, and therefore are the most interesting ones to us. But we do jointly infer these parameters alongside of our cosmology. We also account for the merger rate of our compact binaries. The merger rate model that we use is the Maddow-Dickinson star formation rate model. So this one is also a parametric model that has 3 parameters that control the slopes and the 0-point redshift, or the peak redshift of the merger rate model. And so this is another set of parameters that goes into our inference that is also jointly inferred with the population parameter models and the cosmological parameters. So all in all, from the GWTC 5.0 data set of gravitational waves, we select a subset of 236 compact binaries out of the 390 total. The reason for this subset is that we use a false alarm rate threshold of 1 per 4 years. So this is just to account for, only well-defined and high signal-to-noise events, so that we can avoid problems with noise and marginal detections and so on. With this, we have 235 standard sirens that don't have an electromagnetic counterpart. 4 of these have a potential neutron star component, and the other 231 are all binary black holes. And then we also have the one bright siren with an electromagnetic counterpart, which is GW170817. We actually exclude the massive event GW231123 because it previously had issues with the parameter estimation and the source parameters. It was giving inconsistent results, so we elected to exclude this from our analysis, and we have made tests to show that this doesn't affect the result at all. Here is a cumulative plot that shows the localization area of all the events in different observing runs. As I was saying earlier, the events in O4b are better localized than previously. This is because the Virgo detector was back online in O4b after missing O4a. And the addition of the third detector means that our sky localizations for all of our events were much better than they were in O4a. And so this is denoted by the blue line on this plot. The orange line is the previous first part of the fourth observing run, O4a, and the sky areas of these events were much larger than what we see in O4b. And this has a large effect on the cosmology results because better localization means better constraint on our cosmological parameters. So that's all the information about the gravitational wave data. Now let's talk about the galaxy catalog data. So we use 2 different galaxy catalogs here. The first one is the GLADE Plus galaxy catalog. This one is the same catalog that is used in previous LVK analyses. It has nearly full sky coverage across the entire sky. It includes about 1 million galaxies that are combined from multiple different surveys that are both photometric and spectroscopic redshift. But the goal of this survey was to combine everything we could in order to cover a very wide region. So you can see here on this plot that there are 20 events that are plotted in red. These are the localization area of our best localized events in O4b. And so these are what are expected to be the most consequential for our results. And this catalog covers the area of these events quite well. And so this is the kind of the standard for LVK analyses, at least in the past. And it's continuing now into this analysis as well. But we add a new galaxy catalog. This one is the Dark Energy Survey, or DES catalog. This catalog has a bit of a different philosophy. It covers 1/8 of the full sky, so a much smaller area than the previous GLADE Plus catalog, but includes 350 million galaxies that all have photometric redshifts. So it goes much deeper in distance than the GLADE Plus catalog, even though it's a much more limited survey. And so This is a new addition for this version of the LVK analysis, and we compare what kind of results we get from both of these catalogs. To compare these catalogs, I want to show these plots just to emphasize this comparison. What we're really doing is comparing a wide and shallow catalog, which is GLADE+, to a limited and deep catalog, which is the Dark Energy Survey. On this left plot here, this is a plot of the completeness as a function of redshift. So the completeness fraction is a number which tells you what fraction of galaxies that actually exist in the universe are included in the galaxy catalog based on the depth of the galaxy catalog. And so the blue line here is for GLADE+. This means that GLADE+ is fully complete at very close redshifts, but then drops off very sharply to past 50% and almost 20% when you get out to redshift of 0.1, which is still quite close in cosmological standards. The DES survey, by contrast, is the orange line here, and it stays at 100% completeness for most of the redshift range that we are concerned about. On the right-hand plot, I want to go into a bit of an explanation about what this is saying on this plot, because it's also consequential for the results. But this is a plot of the GW event distribution in redshift. So in the red line here, these are the distribution in redshift of the best 20 gravitational wave events that we have. For this plot only, we are assuming some cosmological parameters like H naught of 70, just for plotting purposes. This does not go into our analysis, but it's useful for diagnostic plots like this. So if you plot the distribution in redshift of the 20 best gravitational wave events, we can then plot the coverage of our galaxy catalogs that overlaps with those gravitational wave events. And so the dashed lines here on this plot, the dashed blue and dashed orange lines, show the two-dimensional coverage. So only the area coverage of the catalog footprints that overlaps with the gravitational wave event areas. And then the solid lines here, the blue and the orange, denote the three-dimensional coverage. So the three-dimensional overlap between the depth of the catalogs and the gravitational wave event volumes as a function of redshift. And so what ends up happening is that if you take the area under all of these curves, you can find out what percentage of your gravitational wave event volumes is actually covered by each catalog. And what we find is that both catalogs cover a similar percentage of the cumulative gravitational wave event volumes, which means that we actually expect them to give us similar results, even though they have different philosophies about which galaxies to cover and how much of the sky to cover. And so now I'm going to pass it on to Alex to talk about our results.
Okay, great. Thank you very much, Isaac. Isaac's done a great job of setting me up now for the very exciting task of talking about our results. So we start here with our flat lambda CDM results, which is basically our headline set of results. And these are all obtained using our fiducial model. So this is using the FUPOP 4.0 mass model, which you remember as being one of the multi-population models, which uses both neutron stars and black holes, as well as using the DES R-band galaxy catalog. So that was the galaxy catalog that was over a much smaller area of the sky, but had a much higher completeness. So had information to a higher redshift. So just descending through these results we have on the right-hand side. So first off, we have our bright siren result in yellow. That's the yellow curve in the plot. And this is coming from just one event. This is coming from our single bright siren, where we've used the information from the electromagnetic counterpart. And this is actually very constraining, considering it's one event. The next down is from spectral sirens only. So this is using just the mass distribution with no galaxy catalog information whatsoever. This is using 235 events and no electromagnetic information. Below that is our dark sirens in blue. This is now basically the same as the spectral sirens. We use all 235 events. We also jointly estimate the mass distribution of gravitational waves with our cosmology. And here we additionally inject that information from the DES catalog to slightly improve our constraint. You can see that the plot left-hand side, that blue curve is slightly better constrained. It peaks at a slightly higher value than the orange spectral siren curve. And then once we have this dark siren result, and then we combine it with our bright siren. So in black is our overall result using both the dark and bright sirens. So this is 236 gravitational wave events in total, including electromagnetic information from the counterpart and also galaxy catalog information. And this is an 11% constraint on the Hubble constant. And just for reference, to give you an idea, so in pink there is Planck. So this is information coming from early time physics, coming from the cosmic microwave background. These are the constraints on H0 you get from that, which are very tight. And in green, that's coming from shoes. So this is late time Hubble constant, and this is coming from things that are much nearer by, like supernovae, coming from the cosmic distance ladder. Obviously, our constraints are still broader than these, but we are approaching a more and more competitive constraint. Isaac, if we could go to the next slide, please. Thanks. So yeah, just a reminder that GW170817 is still the only EM information we have available, so we only have one bright siren. But also pleasingly, the inclusion of the DES catalog improves our constraints by roughly 7%. You may also be wondering how our constraints improve when we use GLADE Plus, which was the broader catalog over the full sky with much lower completeness. And we find that it improves our constraints by roughly 5%. So slightly less, but still giving us a bit of extra information. Okay, next slide, please, Isaac. So yes, as Isaac noted, when we do our spectral and dark siren analyses, we jointly estimate cosmology along with the population parameters. This means our parameter space gets quite large quite quickly. In fact, for the full pop model, when we include cosmology, we find that we have 22 dimensions, 22 different parameters that we need to constrain. And here we have a corner plot where the diagonal plots are basically the one-dimensional results, and the ones on the off diagonal are the 2D probabilities between these sets of parameters. And these are showing H0 in the left-hand column, and then a set of interesting astrophysical parameters from our population as well. And what we're looking for is basically the correlations between these and H0. So what we find here is that the peak locations, which we call mu G low and mu G high, are most correlated with H0. You can see this because they have this kind of diagonal shape to them, which means they're giving us quite a lot of cosmological information. However, we do also find that there is not a significant correlation with either the maximum mass, which is in that bottom left corner. There's a slight slant, but in general, it's not super informative. And also, we don't find any correlation at all, really, with the gamma parameter, which is the low redshift slope of Maddow-Dickinson. As I say, this is a reduced corner plot. There's lots of other parameters in here, but some of them are unfortunately just not very cosmologically informative. Next slide, please, Isaac. So the nature of this analysis is that we don't know exactly the shape of the population. So this motivates doing a little bit of systematics testing by trying out different population models, sorry, and seeing how that affects our results. So in the left-hand part of this plot, we see the impact of using different mass models. So we have three mass models here. We have the multi-peak, which is designated the MLTP. This one is using only binary black holes. As you can see here, compared to the other two, which are our multi-population models, those which use both neutron stars and black holes, the multi-peak gives us slightly worse constraints on the Hubble constant. The overall distribution is a bit broader. We also find that when we include some extra features, the full pop 3 peaks has some extra features for high mass black holes. We find that these extra features slightly improve our constraints. They narrow the shape of the posterior, this distribution a little bit more, but not very significantly relative to our fiducial model, which is the full pop 4.0. And when we consider model selection, so we use Bayes factors, we use Bayesian evidence to compare our models, we find that the Bayes factors that come out of our analyses don't significantly prefer either model, either the full pop or the full pop 3 peaks, which is why we use the full pop 4.0 because it was used in previous LVK analyses. In the right-hand plot here, we also do an additional type of population modeling, which is looking to constrain the spin distribution. So another parameter, intrinsic parameter of these gravitational wave events is their spin. The spin modeling is done only for the binary black holes. So this is using the MLTP, the multi-peak model, and we add these 2 additional models, parameterizing the spins either just as a Gaussian or using a transition mass to provide an extra cosmological feature. And we do find that in general, the Bayes factors, when we do model selection, prefer when we model spins, but it doesn't have a huge effect on our Hubble constant measurement. We find it gives us a slight shift and actually a slight broadening of our posteriors, but we include this for robustness. Next slide, please, Isaac. Thanks. So another thing that we look into when we consider our systematics is different ways of using our galaxy catalog information. So in the bottom left corner, you can see we have this expression. So WGAL is the weights that we provide each galaxy, and we weight each galaxy proportionally to the luminosity. So it's to the power of epsilon, and we have 2 different epsilons. We have epsilon is equal to 1, so directly proportional to the luminosity of the galaxy, or epsilon equals 0, where each galaxy is uniformly weighted. Both of these are quite informative choices in their own way, because either we're saying that we don't care at all what kind of galaxies our gravitational wave events are coming from. We have no idea. Or we're saying that we quite strongly favor more luminous galaxies, which we might consider to be, for example, galaxies that are forming more stars. So both of these are quite astrophysically informative choices in a different way. For our fiducial results, we actually use the epsilon equals 1, so the proportional to luminosity weighting case, which is on the left-hand side, the Des R-band curve, orange on the left-hand side. And you can see that in all these cases, the dark siren results, so the galaxy catalog results, have improved our constraints relative to the spectral siren, which is in the black dashed line. Additionally, the Des R-band is more informative than Glade Plus for both types of weighting, so epsilon equals 1 and epsilon equals 0, because it has a sharper posterior. But additionally, when we consider our model selection, we calculate Bayes factors from our evidence between all of these different analyses, and we find that no catalog shows a significant preference by Bayes factors. So we can't say for certain that any of these 4 different setups are clearly favored by the data relative to one another. Next slide, please, Isaac. Great. So another thing that we do, apart from just constraining H0 when we're considering flat lambda CDM, is also consider departures from general relativity on cosmological scales. We call this modified gravitational wave propagation, and the reason for that is as follows, which is that in GR, the gravitational wave amplitude depends inversely on the luminosity distance. It's encoded in the signal, and we get this information, we use it in our analyses. But very often in modified gravitational wave propagation models, we instead designate this, rather than being the EM, electromagnetic luminosity distance, we call it the gravitational wave luminosity distance. And we say that our amplitude is proportional to 1 over this. This means that the ratio between these is actually not equal to 1. So essentially what we're going to try and constrain is this ratio of the gravitational wave luminosity distance to the electromagnetic luminosity distance. And we see a departure from general relativity when these are not equal to 1. But however, in general, in our analyses, we assume that gravitational waves are, traveling at the speed of light. And the reason for this is we have very strong bounds from our one bright siren, GW170817. So in the next slide, I'm going to talk a bit more about specifically what models we're using. So we have 2 different parameterizations for our modified gravity models. One which is coming from Horndeski gravity, which is a parameterization of gravity in 4 dimensions. And another, which is basically a phenomenological model, one that doesn't have a strong theoretical grounding, but is used to basically directly fit to the data that we see. So on the left-hand side, we have what is sometimes called the alpha M or CM parameterization. So in our analyses here, I'm going to refer to it as the CM parameterization because CM is the parameter that we actually constrain. And you can see that this is the rate of change of some effective constant, and that when Cm is equal to 0, this whole thing vanishes. This ratio returns to 1, and that means we recover GR. For our more phenomenological model, which is pronounced the chi-naught n parameterization, we have two parameters actually, not just chi-naught, but also this power law index n. But in general, we don't get very good constraints on this. So although it is included in our analyses, we can't say very much about it. But in this case, GR is recovered when psi naught is 1. Okay. Next slide, please. So for our modified gravity results, we do two slightly different types of analyses. So these results you see are using just spectral sirens. They don't include any galaxy catalog information. And the reason for this is that we don't expect that the galaxy catalogs, which are at quite low redshifts, are going to have very much effect on these modified gravitational wave propagation parameters, which tend to be constrained by things at slightly higher redshifts. We use these two different priors, a broader prior in H0 and a narrower prior in H0. Everything else is exactly the same. This is the only difference between these two analyses. And the reason for this is that this broader prior in H0 means that we get much worse constraints on these parameters. Whereas when we restrict the H0 prior to the Hubble tension region, so between sort of 65 and 77 kilometers per second per megaparsec, we find that we really improve our constraints on the modified gravitational wave propagation parameters without fixing the Hubble constant. So we have a couple of corner plots here, and these function much the same as the ones that we've seen before. Just a reminder that the merger rate at low redshift is basically fully described by this parameter gamma, which is what we have in this corner plot here. In both of these, the black dashed line is where we recover GR, and you can see that in all cases we are in complete agreement with GR, and that also we see this quite strong correlation between the propagation parameters, Cm and gamma, and then also between psi naught and gamma. I think the next slide, please, Isaac. Great. So additionally to these corner plots, we can also try and reconstruct this distance ratio, because, as I said before, the thing that we're really interested in actually is this distance ratio. So it can be a bit more informative to look at these parameterizations when we project them into the space where the distance ratio exists. So again, the blue is our wide prior and the brown is our narrow prior. And the top panel is this phenomenological psi naught model. And the bottom panel is this CM model. And you can see that we get much better constraints at lower values of redshift. And these constraints kind of broaden as we approach redshift of 1. Over redshift of 1, we tend to find that we don't really get any meaningful constraints on these. And a big part of that is because none of our gravitational wave data is sitting at a very high redshift or luminosity distance. So hopefully, as our detectors improve and we tend to observe things at slightly higher distances, we should get better constraints on these. But pleasingly, we can say that compared to our previous analyses, or GWTC4, both of these models, we found we can constrain roughly 50% better, which is quite a large improvement. Next slide, please, Isaac. Okay, so lots of information there, but just to sum up, we have presented our dark siren analyses using 235 gravitational wave events from the 5th Gravitational Wave Transient Catalog. And using these dark sirens, we explore a number of different things. We have two different galaxy catalogs. We have DES and GLE+. DES being over a small portion of the sky and having much higher completeness. GLE+ being over pretty much the whole sky, but with much lower completeness. We have three different models for the compact object mass distribution, one that's looking only at black holes and one that is using a multi-population model, including both neutron stars and also black holes. We also look at different host galaxy weighting models by luminosity, as well as looking at weighting these galaxies uniformly. And we find that it doesn't significantly affect our results, and we don't see a significant preference for either parameterization when we look at our model comparison statistic. We also consider these two parameterized models of modified gravity. We find that our constraints on these have improved quite significantly since our previous catalog was released, but we don't find any departures from GR. Overall, our H0 precision has improved quite significantly relative to our last catalog. We've got a 26% improvement, and overall we have an 11% constraint on the Hubble constant. The things that are limiting us at this point, and hopefully will be solved in the future, are things like the number of gravitational wave events. Obviously, the more events we have, the more information we have, we get better constraints on our population parameters. They're more likely to be in galaxies that we've observed, so we'll get a better constraint from this. We also find that events that have smaller sky localization volumes tend to give us more information on the Hubble constant because we can pinpoint their redshifts much more accurately. And working in tandem with this, the quality of our galaxy catalogs. We have two different galaxy catalogs, one which has a full sky, and one which has only a small patch of the sky, which is much more complete. Ideally, what you want is a full sky catalog that is very complete. So possibly some upcoming things like LSST or Rubin or DESI might help us in this sense. And lastly, something that's not on the slide here is it would be very helpful if we observed any more bright sirens. GW170817 is a hugely informative event in that yellow curve. We've only observed one, and actually this catalog is quite an interesting time in gravitational wave cosmology because it's the first time that our dark sirens in blue are actually contributing more information to our overall constraint than the bright siren. But it's very revealing that we've needed almost 250 of these events to match up with just one bright siren. So we would also see a pretty good improvement in our results, I think, if we saw another EM counterpart. And I think I will leave it there, and we have lots of time for any questions. So thank you very much.
Thank you, Isaac and Alex, for the presentation. So I believe a lot of you have questions. So please feel free to use the Q&A feature on Zoom to type in your questions. And if you feel like speaking up, you could also click on the raise hand and I will call you, and then you can ask a question verbally. Okay, as we are waiting for more questions, I will just try to read out some of the questions we got on Q&A, and then our panelists can help us to answer them. So one of the questions we got was among the three methods, the bright spectral and dark sirens, which one have the lowest error for redshift? So maybe we'll have Gregor to help us to answer these questions.
Right. So for that question, usually if we're talking about one event, the bright siren has the lowest error for redshift, because what we do is that we can, like pinpoint the exact host of the gravitational wave sources. And usually when you can say exactly which galaxy has, hosted that source, you can get the best redshift measurement. And now if we put that more perspective in the question, is basically what was asked in the second part, which I forgot to answer, but Konstantin did, is that when you add up a lot of events, what we're seeing is that now, with the number of dark sirens that we have, the overall H0 constraint is getting better, or at least as good as this one bright siren. But if you're comparing one event, one dark siren event, and one bright siren, usually the redshift measurement is better when you have the bright one, because you have only one galaxy and you can say which one it is, basically.
Okay, thank you, Gregor. I see a hands up by Eric. Eric, you can speak up.
Hello? Hello?
We can hear you.
Oh, okay. I'm sorry about that. Um, yeah, I wanted to follow up on the question that I asked in the Q&A, which I'll just read it. And Constantine, thank you for your thoughtful answer. The question I asked was, it's been a perennial problem in galaxy surveys to infer stellar mass from galaxy brightness or even luminosities in given bands or multiple bands, let alone as a function of stellar mass. There can be lots of problems, including dust, dark matter, and several other things. How did you account for these, and how did you get from there to the progenitor population? And I'll leave it for everyone to read Constantine's answer, but I wanted to follow up on that and specifically, I guess, ask is the assumption then that there is a direct correlation, basically one-to-one, between stellar luminosity and the chance that a given galaxy might be the galaxy that the gravitational wave event came from. So you're basically trying to bypass a population model.
Constantine, would you like to take that?
Yes, I can take that. So, I mean, you're absolutely right that in principle, the mapping from galaxy properties to the host probability of a compact binary coalescence is arbitrarily complex, right? So, for example, you'd have to, I mean, even if you were to measure stellar masses, there's a time delay distribution because it takes stars a certain amount of time to like form binaries that merge, right? And so this is really, really hard to do in general. And of course, we're doing, as you said, a huge approximation here. Now, maybe for the technical details, Isaac has a better insight how we go from the raw data to the estimated luminosities, because this is also quite a complex task. I think it's important to highlight how big this effect is in general on the Hubble constant, right? And Alex had this great plot he presented maybe a few slides back, where we compare the weighting of our two. I mean, we have two weighting schemes. So one, right, exactly. So here you have the host probability, right? W galaxy, which stands for weight galaxy. And then this is proportional to the estimated luminosity to some power, right? And on the left-hand side, you have the power, so linear power, epsilon equals 1. And on the right-hand side, you have epsilon equals 0. So there you basically neglect all information you have of the galaxy. And I mean, it shifts slightly, but it's well within the 1 sigma. So although in principle it could matter, and it would probably matter in the future with more observations, at the moment, this systematic seems to be quite small.
Okay, so basically, right now we're not at the level where we can actually ask this question, I think is the right way to say this, because, from my point of view as an observational astronomer, these are things that uh, immediately come to my mind. And, the vast majority of these gravitational wave events are very, very sensitive to the upper end of the stellar luminosity and really stellar mass function.
Right. Yeah. I mean, I think you could indeed reformulate this question, right, and put it on its head and ask, can we learn something of the mapping of galaxy properties to this host probability? But basically, we're quite far from that at the moment, if that was your question.
Yeah, and 100% on what you just said. Thanks.
Okay, I see another questions on the Q&A. Hold on. Okay, okay. So there's a question asking, when will our method produce comparable uncertainties to either Planck or Hughes? And I see Bergrad, you're answering, so maybe you can speak up for your answer.
Yes, I mean, well, I will say that first. Disclaimer, the answer is not, like we don't have the perfect answer for that. What I'm trying to argue in the chat was that indeed that's, the question everyone is trying to answer, as everyone is expecting gravitational wave, to at some point like show up between Hughes and Planck for the Hubble tension. But I guess my answer will be the following, and probably you won't like it, but first, it depends on how lucky we are, because we, thought that we would have many more bright siren events, and with the better estimate of BNS mergers that we have, it's still, like as likely that we have none or we have more in the future. If we do, with the, like prospective study that have been done by several groups, also outside of LVK, a few of these could drastically, like get those error measurement on H naught down. I don't remember if it's exactly up to the uncertainty level that Planck and Hughes have. Maybe not. Maybe we need more than 10 for that. But then you can also say, okay, if we do not consider those bright sun events, because maybe we won't have any to solve the Hubble tension, or at least get, like percent level measurement on H naught, what we can say is that probably we need to wait for next generation gravitational wave detector like Einstein telescope, or maybe LISA, or the American project Cosmic Explorer, to get thousands and thousands of detections that can be used as spectral sirens, and not as bright sirens or even dark sirens, to get those error on H naught down. So yeah, sorry, I cannot really give you a date. I think nobody really can. Yeah, it depends on what we detect at the end of the day.
So maybe I can add a little bit to the answer. So I think we're talking about maybe percent level of constraint, few percent level of constraint. Next few years with all these different standard siren methods combined. And the major role of the standard siren measurement for this Hubble tension is actually mainly not to compete with the precision measure by Hughes or Planck, because it's difficult, but we are trying to produce an independent measurement so that we can possibly say something about this tension. So I guess our focus is slightly different, not trying to compete with the precision, but see where we actually lie at with a few percent level of precision, if that help answer the questions. Okay, so I see another questions here at Q&A. So this is questions asking about whether or not our gravitational wave data is actually distributed relatively isotropic on the sky. Let me see. Would Alex or Isaac, would you like to take this questions?
I can take this one. So in general, yes. We do see that our gravitational wave distribution is isotropic. There is a slight caveat to that, which is dependent on the positions of the detectors themselves. So there is a slight gradient across the whole sky, which is mostly declination dependent, which is just based on the triangulation and the sensitivity of the detectors. And so I don't remember exactly what level this is, but it's to the level that it doesn't show up very much in our measurements.
Thank you, Isaac. So I see a hand up from Anya. Anya, would you like to speak up?
Yes, can you hear me? Hello?
Yes.
Okay, so thank you for the presentation, Isaac and Alex. I just have more a comment than a question. That you were, when you were showing the results of the modified gravity constraints, you were calling the alpha M parameterization or something for density theory, but in fact, that particular feature appears also for more general modified gravity theory for beyond or density. Basically, it's related to the running of the Planck mass. So in principle, you are constraining not just Ordensky theory, but also beyond Ordensky theory, which is this running Planck mass. So more than a question, maybe it's just a comment. Anyway, thank you.
No, that's fair enough. Thank you. I have to admit, I'm not an enormous expert on modified gravity, but
Sure. No. It's just to show that it's even more interesting, the result. Yeah, thank you.
Yeah, no, that's good.
Yeah, I just see a new one on Q&A. So it says that since you have a range of redshift sources and apply with a similar techniques, can you see any evolution of the value of H naught as a function of Z? Constantine, I see that you're trying to answer, so would you like to just speak up?
Yes, sorry. So indeed, there are some works that explore the Hubble rate as a function. I mean, so the Hubble rate is obviously a function of redshift, and if you assume a flat lambda CDM cosmology, then this is quite a rigid function that depends, as Isaac said, on the matter content and on the energy content in dark energy, for example. But of course, the universe might not be flat lambda CDM. And so the paper I've posted in the chat is exploring the evolution of the Hubble rate in a weakly modeled, and some people call it non-parametric way. Yeah, if source capital Z here is indeed the source redshift, because some people also use it as metallicity, and then my answer was maybe not accurate.
Is there anything else to add by our panelists for this question? Okay, if not, since we are 5 minutes past the hour, I hope we answered most of your question and you got what you want to hear or listen to learn from this paper. I hope you find our paper interesting. Again, maybe you can check out our paper on arXiv, and also the data are available. I think we will also be happy to take more questions if you send it email to the collaboration outreach. Okay, so I would like to thank all the presenters and the panelists today, and thank you for your attendance. Have the good rest of your day. Thank you.